Those unfamiliar with all things astronomical sometimes get a little confused when they hear about the closest star to Earth. Alpha Centauri? Beta Centauri? Proxima Centauri? Which star will be the right one? What do you say we go for a ride over there to remove any doubts about it? We often hear that Proxima Centauri is the closest star to the Sun, and thus to Earth. But it is important to point out that this red dwarf is actually part of a triple system that is made up of 3 gravitationally bound stars named Alpha Centauri as a whole. To the naked eye, this system appears as a single very bright star, visible only from the southern hemisphere in the constellation Centaurus. In reality, the system consists of a pair of stars, Alpha Centauri A and Alpha Centauri B, which are very close to each other. In addition to these, there is a third one, a much more distant and less luminous red dwarf called Proxima Centauri, Alpha Centauri C, which makes a very wide orbit around the main pair. That Alpha Centauri is not a single but a double star has been known since December 1689. In fact, it was around that time that Father Jean Richaud, a French-born Jesuit astronomer, discovered 2 components separated by an angular distance of a few seconds of arc. The first suspicion that this was not simply perspective proximity, but that the 2 stars were gravitationally linked, came in 1709, following the observations of another religious father, Louis Fouillet. But final confirmation came with astrometric measurements made in 1752 by Abbot Nicolas Louis de Caille, who detected the position of the components and their shift from Fouillet's first observations. Alpha Centauri, also known as Rigel Kentaurus or Rigil Kent, or more rarely as Toliman, is the brightest star in the Centaurus constellation and the 3rd brightest star in the night sky to the naked eye after Sirius and Canopus. Today we know that the primary star in the system, Alpha Centauri A, is a yellow star very similar to our Sun, slightly larger and more massive, while the secondary component, Alpha Centauri B, is orange, slightly smaller and more massive. However, both components are stars whose age, according to current models of stellar evolution, would range between 5 and 6 billion years, making them the same age or slightly older than the Sun. The 2 components orbit the system's center of mass for a period of 79.9 years. Their paths are on a fairly eccentric orbit, with their distance to each other ranging from a minimum of 11.6 astronomical units. Recall that an astronomical unit is the distance between Earth and the Sun, which is about 150 million kilometers, to a maximum of 35.6 AU. The high inclination of the orbits with respect to Earth, however, makes the detection of their mutual displacements over years uneasy and introduces considerable variations in their angular separation, which in about 40 years can vary from a minimum of 2 to a maximum of 22 arcseconds. The discovery that the Alpha Centauri system is also the closest to us was by the Scottish astronomer Thomas James Henderson, who measured the trigonometric parallax of the system between April 1832 and May 1833, finding a distance of 4.35 light years. The record lasted only 85 years, however. In 1915, in fact, a star was detected near Alpha Centauri practically out of nowhere, a very faint star indeed, which would not only shortly thereafter stand as a candidate for the role of the 3rd component of the system, but would snatch from Alpha Centauri the scepter of the closest star to Earth. The scene of the discovery this time was South Africa, and the key figure in the story was Robert Innes, also a Scottish astronomer and director of the Johannesburg Astronomical Station. Examining at the comparator 2 photographic plates taken in 1910 and 1915 respectively, and meticulously scanning the area around Alpha Centauri, Innes spotted a couple of degrees away a star 200 times fainter than the faintest stars observable with the naked eye, characterized by a proper motion very similar to that of Alpha Centauri. What could it be? Innes thought it might be a low-mass star gravitationally bound to the Alpha Centauri double, even closer to Earth, albeit by a small amount. So much so that he was the one who ventured to put the name Proxima from the Latin word for near. An intuition, fortunately for him, that was also confirmed in 1928 by the studies of American Harold Alden, who found a distance of 4.3 light years, slightly less than that of Alpha Centauri. In the years that followed, measurements became increasingly precise, and Proxima was able to be classified as a red dwarf, the probably most common stellar type in the Milky Way, at the lower mass limit of its category. Scarcely luminous and relatively cold, Proxima has little more than the age of the Sun, about 4.8 billion years, and a surface temperature of only about 2,900 degrees Celsius, compared with 5,770 degrees on our star. As a result, its habitable zone, or Goldilocks zone, that is the circumstellar belt where a planet could have liquid water on its surface, is only 7.5 million kilometers away from the star. In 2002, the Very Large Telescope's optical interferometer allowed direct measurement of its angular diameter, which turned out to be 1.02 thousandths of a second of arc. This resulted in a diameter of just over 200,000 kilometers, or about 1/7 that of the Sun. Only 1.5 times the diameter of Jupiter, just 15 times that of Earth. Its mass, however, was estimated at 12.3% of that of the Sun, much higher than would be expected for an object of this size. So much so that its average density was found to be much higher than that of the Sun, 57 grams per cubic centimeter versus 1.4 grams. Its total luminosity, encompassing all wavelengths, was found to be 0.17% of that of the Sun, although when observed in visible light wavelengths, the percentage is reduced to 0.0056%. More than 85% of the star's energy is in fact radiated in infrared wavelengths. The most recent data, obtained from interferometric measurements made in 1999 by the Hubble Space Telescope, indicate for Proxima a parallax of 0.7687 arcsec, corresponding to a distance of 4.246 light years. The fact that it holds the record for proximity to the solar system is not the only peculiarity of this tiny red dwarf. But before examining its physical characteristics, it is, however, necessary to say a few words about its connection with the Alpha Centauri double system. In fact, although it is currently referred to as Alpha Centauri C, i.e. the third component of the system, it is not yet certain that Proxima is really gravitationally bound to the other two stars. It may sound strange, but the possible link has not yet been unequivocally proven. The doubts lie in the fact that if Proxima were also part of that stellar ballet, we would be in the presence of a rather anomalous system, characterized by a normal double star around which a red dwarf rotates at a distance of at least 8,700 AU or 0.13 light years. This would imply an orbital period of more than 500,000 years, effectively making the detection of relative motions, and thus orbit confirmation, incredibly complicated. On the other hand, supporters of the triple system hypothesis could invoke a simple statistical consideration in their favor: the probability that there could be independent stars characterized by a very similar proper motion migrating through space at such a small mutual distance is very low indeed. They might simply belong to the same stellar system, but it would be unlikely that their proximity, not just perspective, would also imply a real physical connection. But there is more. The Alpha Centauri system is not just made up of stars. In 2016, in fact, what many astronomers thought was highly unlikely from a statistical point of view happened: the detection of an Earth-sized planet orbiting the closest star to Earth. The stuff of science fiction, almost a sign of destiny, as if the universe wanted to tell us, as the first step to the cosmos, you Earthlings were lucky enough to have a large moon very close to your planet, and now we also give you the second step: a world at your disposal around your nearest star. But things, as we are about to see, are not quite like that. Proxima B, as it has been tentatively cataloged, is probably a rocky planet whose minimum mass could be 1.17 Earth masses. This value, along with other estimated values, brings it to a 6th on the list of exoplanets most likely to have a rocky composition, with an Earth Similarity Index (ESI) of 0.87. This value ranks alien worlds based on their similarity to Earth, according to radius, density, escape velocity, and temperature, but does not take into account all factors that might influence their habitability. In any case, we still know little about Proxima B. Its orbital inclination is unknown, as its exact radius, and therefore its mass could also vary greatly. Although Proxima B is about 20 times closer, 7.5 million kilometers, to its star than Earth is to the Sun, thanks to the red dwarf's low temperature, it actually receives almost the same amount of energy. This means that the surface temperature could favor the presence of water in a liquid state and support the development of life. However, the planet is likely locked in a synchronous rotation due to its proximity to the star. That is to say, it could always show the same face to Proxima as the Moon does to the Earth. This feature could result in an important diversity between two hemispheres, while the entire planet would be bombarded by the red dwarf's energy activity, with an estimated amount of X-rays about 400 times more than Earth receives from the Sun. In short, you may have already figured it out. Proxima B orbits in the habitable belt of Proxima, but it may not be as hospitable as we imagined after all. In fact, observations made around the same time as the discovery recorded a flare so intense coming from the red dwarf that it was briefly visible to the naked eye. Flares are violent eruptions of matter that explode from a star's protosphere, releasing large amounts of energy. They are often accompanied by large plasma ejections known as coronal mass ejections. These elements determine the space weather of the system and play a key role in the habitability of a planet and the eventual evolution of life on it as we know and understand it. Under extreme conditions, superflares could wipe out a planetary atmosphere and heavily lash a magnetosphere, even to the point of leaving the planet's surface exposed to deadly radiation. During superflares such as those observed, the radiation dose without protective ozone would be 65 times greater than that needed to kill 90% of the most ultraviolet-resistant organisms on Earth. And according to statistics, Proxima Centauri is estimated to produce flares of this magnitude at least 5 times a year. Before we move on to the final question, how long will Proxima retain its title of closest star to Earth? Be sure to stay tuned afterwards if you haven't seen our early release on From Earth to Proxima Centauri in 20 Years, the project Breakthrough Starshot. According to recent studies on the motion of near-Earth stars, Proxima came to beat off competition from other stars about 32,000 years ago, and it looks like it will retain this characteristic for at least another 25 millennia. But there is something even more interesting. In that time interval, in fact, the absolute value of its distance, along with that of Alpha Centauri AB, will gradually decrease by about a light year, touching the minimum value of 2.9 light years in 27,400 years. From that date on, Proxima will pass primacy to the Alpha Centauri AB pair, which will hold the scepter for about 8,000 years, before momentarily ceding it to Ross 248 and then to Gliese 445, before taking it back for good in 50,000 years. While Earth is at no risk whatsoever from the approach of the two red dwarfs, quite more problematic might prove to be for our very distant great-grandchildren to find two solar mass stars, Alpha Centauri A and B, less than 3 light-years away. Our outermost Oort cloud would inevitably be disrupted, and this could translate into tens of thousands of comets hijacked from their normal orbits and destined in the span of a couple million years to break ruefully into the planetary region of the solar system. In short, even if we are talking about scenarios that are lost in the really distant future, really bad times could be brewing for our beloved Earth. In any case, the Proxima Centauri system is still all to be explored, and Proxima B may not be alone. Several clues point to the presence of a second planet, Proxima C, perhaps a gas giant with a ring system. But for now, it still remains a candidate. Unfortunately, awareness is growing about the near impossibility of being able to trust a red dwarf as restless as Proxima, and so hopes of having finally found our ideal planet B are growing dimmer and dimmer. But while some hope to be able to embark on an interstellar voyage to check out the planetary system closest to us in person, if one wants to stay with one's feet on Earth, it really has to be said, one must hope for next-generation telescopes and observatories. However, the secrets of Proxima B will not be easy to grasp, even for the James Webb Space Telescope. The JWST canon has already acquired direct images of planets around nearby stars. However, Proxima Centauri B orbits so close to its star that we expect the light reflected or emitted from the planet's surface and atmosphere to appear fully blended with the star's light from our vantage point. The thing is, in short, it will not be easy even for our best soldier in space, and we may have to wait until the completion of the 39-meter telescope under construction in the Chilean Andes to really know more at the end of this decade. From Earth to Proxima Centauri in 20 years? the Project Breakthrough Starshot. In 2016, the La Silla Observatory in Chile identified Proxima B, the closest exoplanet known to us today. It orbits in the habitable belt of its own star, Proxima Centauri, a red dwarf located 4.2 light-years away from us, in the direction of the Centaurus constellation. Proxima Centauri is part of the Alpha Centauri system, a triple system consisting of a yellow dwarf and an orange dwarf very close to each other and from Proxima. Proxima is a red dwarf, probably the most widespread stellar type in the Milky Way, dim and relatively cold. It's a little more than the age of the Sun, about 4.8 billion years, but a diameter that is only 15% that of the Sun and a surface temperature of only 2,725 degrees Celsius, compared to 5,725 degrees Celsius of our star. Consequently, its habitable zone, that is, the circumstellar belt in which a planet could have liquid water on the surface, is very close. It is located about 1/20th of the Earth's distance from the Sun. For example, Proxima B, which with an orbital period of 11.2 Earth days is within this zone, would be a hot world if it was around the Sun. Even if located inside the habitability belt, it is by no means certain that Proxima B is actually habitable, due to the intense activity of its star Proxima. In fact, red dwarfs are known to manifest sudden and random flares, even very powerful ones. Flares are violent eruptions of matter that explode from a star's photosphere, releasing large amounts of energy. They are often accompanied by large plasma ejections known as coronal mass ejections. These elements determine the space meteorology of the system and have a fundamental role in the habitability of a planet and the eventual evolution of life on it as we know it. Under extreme conditions, superflares could wipe out a planetary atmosphere and lash a magnetosphere heavily, pushing it back until it leaves the planet's surface exposed to deadly radiation. According to statistics, it is estimated that Proxima Centauri produces flares of this magnitude at least 5 times a year. Everyscope, a series of small telescopes that observed the stars in the southern hemisphere, detected a superflare that made Proxima 70 times brighter in 2016. Again, a very intense flare by Proxima Centauri was registered on March 24, 2017. The brightness of the star increased by 1,000 times in only 10 seconds. The brightness increase was so big that Proxima became visible to the unaided eye for a short period. Given these premises, if there was an atmosphere around Proxima B, it probably didn't survive the likely activity of Proxima, while on our planet the ozone layer absorbs harmful ultraviolet radiation. On Proxima B, assuming it has no magnetic field, 90% of the atmospheric ozone would be lost after only 5 years of stellar activity. The results of several simulations carried out by a team of researchers led by Christophe Lovis of the Astronomy Department of the University of Geneva showed that without ozone, the surface of Proxima B would be devoid of protection against UV rays. During superflares, such as those observed, the radiation dose without protective ozone would be 65 times greater than that needed to kill 90% of the most resistant organisms to ultraviolet rays on Earth. Despite these features, would you like to visit Proxima B? Let us know in the comments. But what do we know about Proxima B today? It's probably a rocky planet whose minimum mass could only be 1.17 Earth masses. This value, together with other estimates, brings it to 6th position in the list of exoplanets that are most likely to have a rocky composition and keep liquid water on the surface, with Earth Similarity Index, ESI, equal to 0.87. This value classifies alien worlds based on their similarity to the Earth, as a function of radius, density, escape velocity, and temperature, but does not take into account all the factors that could affect their habitability. In any case, we still know little about Proxima B. Its orbital inclination is not known, as well as its exact radius, and therefore also the mass could vary considerably. This means that the planet might be rocky like the Earth or frozen like Neptune with a thick atmosphere of hydrogen and helium. Although Proxima B is about 20 times closer to its star than Earth is to the Sun, it receives comparable energy. This means that the surface temperature could favor the presence of water in a liquid state, if there is any, and support the development of life. However, it is likely that the planet is stuck in synchronous rotation due to the tight orbit around its star. That is to say, it always shows the same face to Proxima as the Moon does to the Earth. An important dichotomy between the two hemispheres could arise from this feature while the entire planet is bombarded by the energy activity of the red dwarf, receiving an estimated amount of X-rays about 400 times greater than that which the Earth receives from the Sun. Nonetheless, the Proxima Centauri system remains one of the most intriguing to study and one of the most coveted for future extrasolar exploration. The planetary system of Proxima Centauri has inspired several projects. Among the best known, the Breakthrough Starshot, also born from the Breakthrough Initiatives. Starshot is a research and engineering project announced in 2016 and born to develop a fleet of sailing interstellar probes and laser propulsion. It was founded by Yuri Milner, Stephen Hawking, and Mark Zuckerberg. In 2017, NASA also proposed a probe to look for biosignatures on the planets around the stars of the Alpha Centauri system. The launch, taking place by 2069, would celebrate the 100th anniversary of the Apollo 11 mission. Another idea to study Proxima B more closely is the Starshot concept. It involves the launch of a mothership that transports small spacecraft, a few centimeters in size, to the outside of Earth's orbit. From here, a laser beam coming from the ground will accelerate the 4x4 meter sails connected to the microprobes up to 100 kilometers per second to the power of 2. Thanks to these probes, it will be possible to reach and visit the planet Proxima Centauri B in about 30 years and capture an image of high quality sufficient to fully understand the surface characteristics of the planet. A swarm of about 1,000 units is assumed to compensate for the losses caused by interstellar dust collisions while navigating to the planet of interest. In a recent detailed study, astrophysicist Chai-Thiam Hong and his collaborators found that mitigating collisions with dust, hydrogen, and cosmic rays may not be as serious an engineering problem as one might think. Using our current technology, a trip to Proxima Centauri for a probe with the same characteristics as the New Horizons, the probe that recently visited Pluto, Ultima Thule, and is now entering the Kuiper Belt, would take about 78,000 years. But projects like Breakthrough Starshot or similar would give a big boost to the development of new methods of space propulsion and new technology for miniaturization of cameras and other electronic components, because it is certainly cool to travel to infinity and beyond, as Buzz Lightyear said in the Disney movie Toy Story, but it is equally so to look for applications that are unthinkable today, useful for improving daily life. What if one day you want to send a human crew to explore Proxima Centauri B? In this case, the problems to be faced would increase dramatically. Some researchers have tried their hand by analyzing some of them. As for the timing, the theoretical speed data of the next Parker Solar Probe, launched on August 11, 2018, were used. It is expected that this will be able to reach a speed of about 724,000 kilometers per hour, or 0.067% of the speed of light. Only this data should make us think a lot. In fact, a simple mathematical calculation is enough to understand that a possible trip based on this technology of thrust could last about 6,300 years. In the event that it is decided to send a human expedition to Proxima Centauri B, it will be necessary to consider a substantial generational change to be hosted inside a spaceship designed for colonization. According to the researchers, the minimum number of humans to send would be 98 people, split equally between men and women. However, this may not be as accurate. To calculate it, the researchers used a type of Monte Carlo simulation called Heritage, which allows to identify the most likely scenario, obtaining it through the consideration of various iterations between the variables. Taking into consideration the natural and accidental deaths, infertility, and the increase in consanguinity, it turns out that the journey represents an unknown factor, especially in relation to its length. Then there would be a serious problem of crew sustenance in the long term, which would require a control in both directions of the berths, with restrictions based on the maximum number of the population, not to mention the energy problem. The most critical element of all is undoubtedly the creation of a habitat of a few cubic meters, in which astronauts should spend the rest of their lives. It would be impossible for them to even return to Earth once the scientific exploration of Proxima B is finished, unless they radically increase the capacity of the spaceship nuclear reactor to supply energy. But this would most likely lead to exceeding the limits of size and mass useful for launch. If you were astronauts traveling to Proxima B, How would you feel at the thought that you will never return to Earth again? Let us know in the comments. In short, a crew of heroes would be needed for such a mission. The astronauts must be selected not only on the basis of technical, scientific preparation and physical skills, but above all on the basis of character skills. It takes exceptional people to leave the Earth knowing they cannot go back, ready to spend decades locked up in a flying box of a few cubic meters. Their solitude would be absolute. Moving away from the Earth, they would see the latency time continuously increase between the sending of a message and the arrival of the relative response, a time that would gradually expand to become whole years. How would you feel to wait so long for a response to your message to Earth? Write it in the comments. The effects on the human body of years spent in space are unknown. All the experiments carried out so far have been limited to a year or so spent in low Earth orbit aboard the International Space Station, as in the case of the experiment involving the astronaut twins Mark and Scott Kelly. We do not know what adaptations and above all what physical, cognitive, and psychological damage can affect human beings forced to remain in space for decades, locked up with a narrow environment without the Earth's gravity, without the possibility of having contact with other human beings, without direct exposure to sunlight, and without being able to breathe pure air. Furthermore, there is currently no prototype of a space capsule capable of creating an environment in which astronauts can live for long years. An environment equipped, for example, with artificial gravity, micro-greenhouses, or recreational facilities. It is very unlikely that something like this could be produced within a few years. Above all, it is very difficult, if not impossible, that a home for astronauts, the supplies to survive in space for decades, and the scientific instruments to explore new worlds can be crammed within the limits of space and mass that even a super rocket like the SpaceX Starship must comply. All this suggests that a manned interstellar journey will not be possible for at least 50 years, perhaps more. And even when it has finally become feasible, it won't be at the paltry cost of $100 million, but several tens of billions of dollars. Considering the preliminary decades spent on research and development, it will be an undertaking that only a strong international political will can transform into reality. Be sure to join the channel, leave us a like, and click on the bell. You will help us to make products of even higher quality.